sets and events. The argument is, well, multiple things. Sets and not events. That's old. Yeah, events leading up to probability. Never mind, sorry. The argument is that sets and collections of things, they do feature now and then in the elementary school curriculum. And it's also a nice, slower introduction to the probability concept. It's not something at our level that we're going to use in probability all the time directly. That's when things gets a little more complicated, we would. Now and then, it's just a nice, slower introduction. So I'm really only concerned with this set word. A set is just our mathematical word for a collection of objects or things. Those things could be the chairs in this room. That's the set of chairs. The set of people. Or it could be more abstract things. Still, I just have a collection of stuff. Collection of stuff. That's just what we call a set. Okay? These objects or things are called the elements of the set. So if I have the set of chairs in this room, this is one element of that set. Okay. So let's make some examples. Usually, we're a little bit more abstract here, and we often use things like letters and things for the elements of the set because I can tell them apart and they're easy to write. And we'll use capital letters for the names of the sets. So let's say capital A is the set containing, so let's look at sets of lowercase letters of the alphabet. And now we can make some of them. Let's say little a, I want to be consistent with the book, so little a, little b, little c. And when I list the elements in a set, I'm going to enclose them in curly brackets. There is no order here. I could have also named set A the letters C, B, A. Still the same collection of three things. How I list them is irrelevant. There's no arranging or ordering of the elements. So big A and little a are completely different things. Capital B will contain or will be the set of little letters B and C. I just arranged them alphabetically, but it really doesn't mean anything. Let's make some more. Let's make capital C the name for the set C, D, E. I'll try and make pretty curly brackets, but they're going to deteriorate pretty fast. Let's just be honest. And you know, A, B, and C, they always get so much attention. Let's go X, Y, Z. Any letters. You could pick anything. Those are just four sets among millions of them. Many other combinations of things I could have selected, of course. Now there are some concepts. So this is, in a lot of ways, an extension of the number concept. In that I don't have just a single number, I now have collections of things, and I have more variety because of that. So we have some concepts. I will just list them with dots. Two sets are said to be equal only if they have exactly the same elements. So even though there's some similarities between sets, they could share some elements, they are not the same unless they have exactly the same things, no more and no less. So the sets A and B are not equal. They are connected in some way, but they're not equal. For example here, A not equal to B. Everyone happy with that? New, fresh start. So maybe previously you felt, ooh, I didn't ask questions when I was confused, and it resulted in something bad, maybe. Fresh start. Talk all the time. Everyone, all the time. Well, I have to squeeze in some things, but not as much as you think. Okay. I'm going to leave this page because we're going to look at these examples and jump back and forth. So I'm going to make a new page so we don't lose our examples, but they're also at the bottom of page 35. It's nice to have them on the screen though. All right, next concept is that of a subset. I'll put little squigglies under it. Those are the key words. So now I want to have a general statement about sets. Not necessarily these ones. These are specific examples. So I don't want to use these letters. I'll use maybe E and F. We haven't used those yet. So set E, referring to any set. Maybe an example one, maybe something else. Is called a subset of another set F, let's call it, if each element, these are going to be a little wordy until we finish them. There's not that many of them. Each element, I'll say in E, is also in F. We will only have like a few more that are this wordy to explain the concept. And then we're pretty much done. Yes? Is it my writing? In.
In? Okay.
My dot for the I connects with the N. You should be used to this months after months of this. At least there's some consistency to it. If you look back in the videos, all the N's are like that. Sorry, yes.
So they're not equal then? You mean a subset? That would be like.
That's a good question. They could be.
F probably has one.
So let's look at our examples, these four, and see what we can see. But first, something that's typical in math, these words are too many words. We don't hate words. Some words are good, but not too many. So we're going to use a symbol instead of all these words for a subset of, and the symbol is going to look like this. It's like a, no, it's got nothing to do with that. Never mind, that's the symbol. Like a long flat C with a line under it. It's the subset symbol. I don't know what to tell you. So, instead of saying one set is a subset of another set, we use a symbol and they mean the same thing. It's again just a translation. So if I look at my sets here, I could say set B is a subset of set A. Because every element, every letter that B has is also in A. A has some other stuff. I don't care. I can think of it as B is contained in A. So I'm not going to jump too much back and forth. It's at the bottom of page 35, the actual set. So look at that, but I'll jump down to that. Everyone happy why set B is a subset of A? B is inside A. It's contained in it. So this means is a subset of. That B is going to annoy me forever. Subset of. If I look at maybe B and set B and set C, they do have some things in common, but set B is not a subset of C. The little c is in there, but not the little b. Not everything that set B has is in C. So I'll say the words as well. B is not a subset of C. And we will write this, just like equal and not equal, B subset symbol, line through it, to mean not a subset. Everything in the first has to be in the second one. You had your hand up.
Yeah, don't worry about it.
Okay. I never do. As we go, things will sort of perhaps clear themselves up, maybe get worse. You have to, we're not in a hurry, you have to say what you want to say. Yeah.
So if A equals with the little a, and then the other one, so, okay, so.
You want to change these sets?
Yeah, can you go back to the first page? So let's say you have A, B, and C. You have that, so, and the other one only has B, does it work?
Oh, this is gone?
Yeah, with the B.
Then-
Subsets?
Set B is still a subset of A because all its components, all its elements are in the bigger one.
So if B only has a C, then it would be a subset of C.
Then it would be yes.
Okay.
And A.
And A.
And it, all right. Thank you.
In chorus. Yes. But everything the small one, the first one has to feature in the bigger one. However, it doesn't have to be bigger. Connecting to her question. Also, B is a subset of itself. Because everything that B has is in B. So technically, it contains itself. It's a subset of itself. So though I'd like to think intuitively, oh, one is bigger than the other one, has more stuff, it doesn't have to be. Is everything in the left one also in the right one? Yes. Then it's a subset. Though I will admit most of the time the right one has more stuff, but it doesn't have to. Subset. There are only like 4 difficult ones. So this is one of them. Difficult, maybe in terms of newness. Any thoughts or questions on subset? You can of course ask later as well. Next one are 2 smaller ones that I'll mention now. The concept of the universal set. Where? That was supposed to be universal set. Very simply, it's the set containing all elements in question. If I am talking about people in this room, then this section could be a set of people, but all people in question, without any restriction, will be the universal set. If I'm talking about lowercase letters of the alphabet, we're going to use U for universal set, sort of as a reserved letter. It's going to be little a, little b, little c, little d, e, f, all the way down to the end. It literally is the set of everything. In context, of course. In context, it's the set of everything. That's the universal set. And then, in contrast to that, I also have the set of nothing, the empty set. The set containing no elements. We're going to reserve the letter phi for that set. Why? Well, why not? There's nothing. Curly brackets with nothing in it. And it's more beneficial to have a reserved symbol because brackets with nothing in it look strange. And they can easily get messed up. Though you could technically have bracket, bracket, and that's nothing. Yes.
Why would you need to represent something that's nothing?
Why do we have the number 0?
Fair enough. Retract the question.
No, it's a good question. Just to really to make everything be complete. That sometimes there is the concept of nothing. Now, admittedly, that question is really an important question because though numbers were with people for a long time, they had no need for a 0. Babylonians, no need for a 0. Only when they got a little bit more philosophical that they realized that nothingness is as important as something. And there should be a number. No, that's actually true. But definitely the empty concept, the nothing concept was very late to the party. Yes.
The universal set contains all the elements in question. Can it
Yes.
contain more than that? Or is it
There
only
is no
specifically-
more than
There
that.
is no more than that. It's impossible.
There's,
Okay.
it's impossible. So that makes it very important to know what are we working with here. If I'm talking about letters of the alphabet, I can't look at a set of people. It's different topics. Looking at one
I
type
guess
of
what I
thing.
mean is if it has A, B, C, and E, it wouldn't be considered a universal set anymore. It's just a set.
No, even though it's not always said specifically, everything always starts with, this is the stuff in question. Now we're working within that.
Gotcha.
But it's not always obvious, but it's always something I have to be aware of. Okay, so these sort of smaller, easier concepts. Sure. Oop, back it up. So now, let's have some examples here. Is it true? Well, I'll say the following. I'll zoom out so I can see both of these things. Referring to the examples over here, I can say set A is a subset of the universal set. And really, any set is a subset of the universal set because the universal set contains everything. So, if I take any set, regardless of what the topic is, that is always going to share everything it has with the set of everything. So really here I can have any set. It's always going, everything it has will necessarily be in the universal set. That's what the universal set means. Sort of on the opposite end of that, the empty set is a subset of any set as well. Now that's more of a technicality, really, but it can't be anything else, which is why it is. Yes, it doesn't have anything to compare to the right set, but if a set doesn't have elements not in the right set, then it's a subset. There is no element in the left one, the empty set, that I can say, oh, this element isn't in A. It's in everything. There's nothing. Just like I compare 0 as a number to other numbers, there's nothing to compare, yet it's less than the number. It has to be, because it's not more. All right. So I really have an arrangement of sets in a way, not to get too fancy, where the empty set's on one end and the universal set's on the other end. And maybe I have a set B, which has little b and c, right? And sort of an extension, something bigger than that, is set A. And something bigger than set A is U. Now, of course, this is a whole complicated mess of things. When you look at all possible sets, this is just one example. So I can sort of have bigger and bigger sets, one containing the previous one. Not that that's super important at all. So I have the empty set at the left that has nothing, and the universal set at the other end, which has everything. How do we feel about those two so far?
Why didn't you include C?
Because it's not really connected to A and B, right? It's its own thing. It has some things in common, but not others. I don't want to make that diagram messy. It's actually very convoluted.
Okay.
It doesn't fit into any one of these, and they don't fit into C. So it's really its own path, yet it is connected. So don't want to make this worse. This is a very crossover connected thing that's really messy.
Sorry, maybe I should just look at my book, but could those arrows just be written with subset signs, or are we getting there?
It doesn't matter. Yeah.
It does matter, it's, yeah.
The same thing. In the end, when they do these things, they use arrows, but yeah. Because it's part of a larger thing, it's the whole thing. Just to show, some sets are connected by way of subsets. Yeah, it's subsets for sure. Okay, we have, let me just double check. Oh, we have this example. Exercise 5.1. Might as well do it while the subset concept is the most important one. So I'm given the set A, B, C, D. I want to list all the subsets. So the subset concept is not hard at elementary school at all. You don't have to call it those words, you can call it something else, but the concept of making some groups of a larger collection is not a difficult concept. So I could, with whatever words you want to use, ask little Timmy to make subsets of that collection of 4 letters. And you can actually put the 4 Scrabble tiles in front of it and all kinds of things. So it's not a hard concept. What would he do though? If you were to tell him, list all the subsets you can make from those 4 letters. What would he do? Probably. No? You don't have to actually have experience to guess what a kid would do once they understand the question. What would they do? No, they would just randomly start making collections. They would say, well, okay, that was a curly bracket, by the way. I could make an A and a B. I could make a B and a C. I could make a B and a C and a D, and they would just randomly go about their business trying to make different ones. But the danger of that is that I'm not sure if I have them all. I'm not sure when I'm done because I went about it so randomly. The concept isn't hard, but the strategy is really what it depends on to enable me to say at the end, yes, I have them all. My list is complete. I need to have some structure in my list. So what I can do is first say, well, I have the empty set. So this is sort of containing 0 elements. Then I can look at all the subsets I can make containing 1 element. I can just have A. I can just have B. I'll list it over here. I can just have C. I can just have D. Those are all subsets as well. So I'm sort of looking at how many letters will feature in my subset to give myself some structure. Now I know all the 1-letter subsets are done. Then I can look at those that contain 2 letters. Let's put it over here. And say, okay, well, I can have A with B. I can have A with C. I can have A with D. Then that's all of them consisting of two letters that has an A in it. Because A can only be paired with one of the others. I can also pair B with A. Is that a new set?
No.
No, it's not new. So I only need to look forward because there's no arrangement here. B with C is a new one though. And B with D is also a new one. And that's B with everything. I already have B with A up here. B with C, B with D. Is that list complete with two letters? Maybe I'm going too fast. There's also a C and a D that I haven't covered. But because I'm restricting myself temporarily with just two letters, it's a more manageable task. I can look at those, they're not too many, and more easily see if something is missing or if I have them all. Rather than the big question, I'm separating the list into how many letters it uses every time to give myself a chance to check, well, is this portion complete? Then I can move on to containing 3. So I'll start with the obvious A, B, C. And now I want to keep 2 of them the same and just look at the variation in the other one. A, B, and D. And that's all of the 3-letter subsets with an A and a B. So then I'll change the B to a C, and I get A, C, D. Put the others over here. Is there anything that has an A in it that I haven't covered? I'm giving myself smaller little sub-questions to be able to more easily identify when I'm done and when I'm not. So I have A with B, C, B, D, C, D. That's all of them with A. So I'm done with the A, so I can use the B and the C and the D. Is there any 3-letter subset that is missing? Because if I can't convince myself of that question, I won't know if my list is complete. So to help myself be sure I'm done, I'm sort of compartmentalizing the question, doing little bits of it at a time. Each bit is hopefully easier. Who is sure that 3-letter subsets are all there? No, I'm sure. No one else is raising mine. One way, it's not an easy thing to convince yourself sometimes. One way is randomly try and come up with 3-letter subsets with an A, B, C, and D. Anything you come up with is already there. And if you do enough of them, eventually you'll feel better, I hope. Now if I zoom out, is there anything missing for the list of my original question?
Universal?
I wouldn't call it the universal set, but the set of everything that was given. So I could also have 4-letter subsets, which will be the same as the given one. And that's as far as I can go. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. But you can see that if that question was just a little bigger, maybe there were more letters given originally. Randomly going about making this list will not end well at all. I need to have some structure guiding myself to know at the end I have them all. Any thoughts on that? Gotten really quiet. Not
So this probably wouldn't apply to what we're teaching here, but is there an equation that you can do to tell you how many
Oh, of
you
course
should
there is.
have?
Of course there is. And we are unfortunately not going to do it because it gets difficult really fast and we just don't have time. To do all the geometry we want to do, something had to go.
So if I came to your office, you can tell me?
Oh yeah, of course. Yeah. It's something that I've always done, but I couldn't fit everything in. But yes, this is sort of setting me up to thinking naturally that if I have too many of these, this list is going to be immense, and I don't want to make the list. I just want to know the answer. What's the shortcut? And then you get into counting techniques, and it's very nice, but it gets complicated. And coming from part one, let's make things better, not worse. But yes, no, there are.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.